Howdy folks, Mr. Reed here, and welcome to one more question. So what I'm going to be taking a look at right now is doing the simplifying of radicals from something that looks like an entire radical, so the whole number is shoved inside of the radical statement, and we're going to put it in a simplified form, which is a mixed radical where no other piece can be pulled out of the radical. Now, I'm going to do it this time with slightly larger numbers than last time, so we're going to put this video at a medium level. And to go along with that, I'm actually going to give you another way that you can approach these. So last time I did a full factored list. The larger the number is, the more unwieldy a full factor list gets to be. So if you'd like to see a different approach to this and also some slightly harder questions, you're in the right place. So let's get to it. Okay, now, again, I chose a square root and a cube root. Those are typically the ones you'll probably see the most anyway. The same sort of process would work with a fourth or fifth root as well, though. So let's start things off by saying it is the square root of 216. So last time I did a full factor list. This time I am going to create the prime factorization of 216. Now, I have a couple methods of doing that. So if you haven't seen my videos of doing prime factorization, you might think what I'm doing is a little bit weird. You can do the method, whichever method you want. Tree methods are probably the most common, but I like to sometimes use something I call the vertical line method. So the idea there is that I'm just going to divide by primes until I get to something that's prime itself. So divide by 2, and it's going to give me 108. Divide by 2, it's going to give me 54. Divide by 2 is going to give me 27. Divide by 3 is going to give me 9. Divide by 3 is going to give me 3. 3 is prime, I'm done. So that is a 2 times a 2 times a 2 times a 3 times a 3 times a 3. Now, what we're looking for here is actually, it is the biggest square that we can take out. Now, if I have, ooh, that was a bad circling. All right, if I have these two 2's, they make a 4 if I multiply them back together. That is a square. However, I also have these two 3's. When you multiply those together, it gives you a 9. That's also a square. But if I took all 4 of those digits, 2 and 2 and 3 and 3, because it's the same, you can split it basically down the middle. I probably could write them differently. I could say there's a 2 and a 3 and a 2 and a 3. And if I split them down the middle, it would be the same thing on both sides. That means that 6 times 6 in this case would be my 2 pieces of my perfect square, which is going to be 36 when multiplied all out together. Since I can make a 36 and I can take a look at that by looking at these prime factors, I have another leftover 2 and another leftover 3, but I can't pair them up, which means I can't make a perfect square. Because if I pull 1, 2 as a prime factor, I need another 2, because if I don't, then I can't split them into 2 equal groups. There are 2 groups that have the exact same factors. So in this case, I can do that, and we end up getting, oh, well, even though I can, and my perfect squares are 6 by 6, it's the overall factor that I get in the factors are 6 and 6. The perfect square that makes is a 6 times 6 is 36. This is the number that I want. Again, you could get this by doing a full list of all the factors of 216. Although the larger the numbers get, the more awkward, as I think I said, unwieldy factoring that large number will be. Whereas the process of going through the prime factorization is usually one that's pretty tame, even for larger numbers, especially if you have a calculator nearby and you can just kind of go through dividing in 2's and 3's and maybe 5's until you get to something that maybe if you don't recognize the primes that divide into it, that's okay, because hopefully by that time it's a little bit smaller. If somebody's made a real nasty number by taking 23 and multiplying it by 51, I'm sorry, it's going to be ugly if you come across a question like that. But for most of the ones that I give, I don't tend to do that sort of thing. So let's take this 216 and split it up into 36 times, and then it would be the thing that when multiplied by 36 gives you 216. Now, luckily I was starting to panic, but then I was like, oh yeah, it's the 6 that's left over there. So I don't even have to do division this time. 36 times 6 is going to be good. That's what I'm looking for. And so in the end, I can rewrite that like we did last time in the mild video as the square root of 36 times the square root of 6. The square root of 36 is 6. That was the reason that we picked that 36. And then the square root of 6 is left as 6. So we get 6 root 6 as our final simplified answer in the form of a mixed radical. The 6 that's left has a 2, 3, and a 6 as factors other than 1. None of those are perfect squares. They shouldn't be because of the method that we used. There was no larger number that we could make that was a perfect square given the prime factors that we had. So this method lets us know that we don't really have to search anymore. We should be good. So 6 root 6 as the answer for that one. Next up, going to do a cube root example, and that cube root is of 864. Again, I'm going to go through and do my prime factorization kind of the same way. So I'm going to divide by 2, that's 432. I'll divide by 2, that's going to be 216. Haha, that looks familiar. I'm going to divide by 2, 108. Divide by 2, 54. Divide by 2, 27. Divide by 3, 9. Divide by 3, 3. And so again, I get my full list of prime factors. You could probably tell how I made these in the first place. Just multiply a bunch of 2's and 3's. So 2 times 2 times 2 times 2 times 2 times 3 times 3 times 3. Now, we're trying to make cubes this time. So when I am grouping together my values that I'm going to multiply, they have to be in a perfect triplet. So I can give the first number 1, 2, and the second number 1, 2, and the third number 1, 2. I can do that again with my 3's and give the first number 1, 3, and the second number 1, 3, and the third number 1, 3. If I kind of wrote it the same way as I did last time, I'd have like a 2 times a 3, and another 2 times a 3, and another 2 times a 3. So it becomes a value that is a perfect cube because it is 2 times 3, which is 6, times 2 times 3, which is another 6, times 2 times 3, which is the third 6. 6 times 6 times 6. Is that value we had last time, which is 216. So 216 is the perfect cube that I want to use here because it is the largest perfect cube. I have 2 leftover 2's here, but I can't give 2 2's equally to 3 groups to make it a cube. If there was another 2 in this list, I would be able to use that as well, and the overall number itself would be a perfect cube. But that's not the case. So what we're going to do here is write this as the cube root of, oops, I didn't give myself enough space there. My apologies. The cube root of 216 times, I got to think. Oh yeah, it's 2 times 2, which is 4. Now, 4 is a perfect square. It is not a perfect cube, so it won't simplify any further for this cube root situation. What we can write in the end is that this is going to be the cube root of 216 times the cube root of 4. 216 has a nice cube root, that is 6. The cube root of 4 is stuck inside of the radical. So in the end, we have 6 cube root of 4 as our final simplified answer. Again, really shouldn't matter whether you have the dot in there or not. So if you don't write that last line, it probably doesn't matter. You usually won't see the dot multiplier in there though, so I decided to write it one more time without it there. All right, so hopefully you'll find that either by making a full list of factors like I did in the previous video for the mild version stuff, or once the numbers get a little bigger, you write prime factorization and you look for being able to take those prime factors and giving them out to groups that are the same number of groups as the index of the problem that you're currently doing. If you do it that way, again, you just multiply all the numbers that you were able to use in those groups together, all of them. So in this case, 2 times 2 times 2 times 3 times 3 times 3 gives me my perfect cube, which is 216. Pull it apart into 2 separate cube roots, and then simplify the one that we made sure was a perfect cube, get our final answer, we're all done. Hopefully you found that one helpful. If you did, like, subscribe, and as always, take care, folks.